Okay, so we're starting a unit where we're dealing with integrals and multivariate functions. We're going to start by looking back to what is an integral in a single variable function. So we're going to kind of build this kind of Riemannish model again here. So remember that an integral is a device used to find the area between a and b under some function f, right? So that's what we want. And the way we did this is we broke this into partitions, right? So at A is the x0 line, this is some x1 value, x2, and we make more partitions, and then this one is going to be xi minus 1, and this one will be xi, and there'll be more partitions, and then this will be like xn minus 1, and then b will finally be xn, right? And the way we do this is we pick some arbitrary x value for each of these partitions. And this arbitrary x value will be xi star. So all we know about xi star is that it's on the interval between xi minus 1 and xi. And there's going to be one of these for each of these partitions. So this one would be like x3 star, this would be x2 star, x1 star. There's one of these for each of the partitions. And then what we do is we look over here and we say, well, what is the f value for that? And that is going to be f of xi star. So we kind of build a rectangle here to approximate this. And we do that for each of the partitions, and then we just sum up these rectangles. So the area is approximately the sum from I equals 1 to n of the height, f of xi star, times the width. Now the width here we're going to represent as delta x, and that's going to be, let's see, the distance from a to b, so that's b minus a broken into n parts. So that's going to be times delta x. So this is our approximation of the area. And the way I make my approximation better is that I make n larger, right? So if n gets bigger, delta x is going to get smaller, and we're going to get a more refined answer to this. So we've got the drawing, we have the initial estimate, now we're going to refine that down to the notation that we're familiar with. So at the end of our work with the drawing, we got that the area is approximately the sum from n equals 1 to, I equals 1, right? We don't want n and n. I equals 1 to n of f of x sub I star times delta x. Now, I can change that from an approximation to an actual by throwing a limit in there, right? So that's the limit as n approaches infinity of the sum from I equals 1 to n of f of xi star times delta x. Remember, in this, delta x is equal to b minus a over n. All right, so this notation we're familiar with. We can change to I equals 1 to infinity of f of xi star delta x. But since we're going to infinity, we swap out this notation because this now falls under the fundamental theorem of calculus, and I can now say I have the integral from a to b of f of x dx. So this is, in fact, the same as this. However, it's just a more fluid notation with the idea of using an antiderivative. Okay, so we're going to break this into a three-dimensional problem. Okay, so let's get a new picture here. So we have my x, y, and z axis. And we're going to start with a very simple case here. We're actually going to start with making a rectangle as the domain. So we're going to have an a to a b interval, just like you do in the one-dimensional or the two-dimensional case. And then we're going to have a c to a d interval over here, c to d. So this is on x, this is on y. And above this, we're going to start building a surface. So we have a surface above a rectangle. And what we want to know is this chunk that's underneath there, what is its volume? So we're no longer talking about area, we're now moving on to volume. So this region down here in the floor is what we call a rectangle. And we're going to identify that as it's the rectangle with the interval AB crossed with the interval CD. Now in set notation, this looks like the set of all x, y, such that x is between A and B inclusive, and y is between C and D inclusive. So this notation and this are equivalent, and they're both talking about this domain down here in the floor, right? So it's that rectangle between A and B this way and between C and D this way in the floor. And what we want to do is we want to say, if I have some f of x, y surface hanging out above that, what is the volume of this chunk below that surface and above the xy plane? So we can call this piece something like S, where S is the set of all points x, y, z, where 0 is less than or equal to z, is less than or equal to f of x, y, and x, y are in R3, right? But x, y are within our, should not be R3, it should be within our rectangle. X, y are in our rectangle. So S is like this chunk. Okay, so let's talk about how to find that volume in a Riemannish kind of way. Okay, so we're going to just look down at the domain for a second, okay? So this is going to be X, and this is going to be Y, and my domain runs between A and B along the X-axis, and it runs between C and D along the y-axis. So this in here is my rectangle R. So what we're going to do is exactly what we did before. We're going to make partitions here. So this is at x0, so this will be x1, x2. Okay, so we're going to keep moving. We're going to call this one xi minus 1. This one is xi. And then we make more, and then we get out to xn minus 1, and b is, of course, xn. All right, so in the y direction, we do the same thing. C is y1, or y0, rather. Right, so we cut across, we get a y1, a y2. We jump up a little bit. We're going to call this one y j minus 1. We're going to call this one yj. And then we'll get a y m minus 1, and d will finally be y sub m. All right, so the key piece here is this guy, right? Because it's just the piece where going this way, I'm running between I minus 1 and I, and going this way, I'm running between j minus 1 and j. And what we're going to do is we're going to pick some arbitrary point in the middle of that, and we're going to call that point the point xij star, yij star. So every one of these little rectangles is going to have some arbitrary point chosen in the middle. And why does it matter? Not matter the point, because eventually I'm going to let n go to infinity, I'm going to let m go to infinity, and these little tiny rectangles are all going to squeeze down to being that point. So what we need to do is we need to add up all the heights. So the height above that point is f of xij star, j star, yij star. So that's the height above that. And if I take the height above this, I'm going to get a prism, right? That prism, so I'm going to get like a prism hanging out above this, right? The height of that prism is this. Its area is going to be like delta x times delta y, where delta x is b minus a over n. Delta y is going to be d minus c over m. So that'll give me the area of the base times the height will give me the volume of that little prism above that square. And then I just got to count the ones over top of all the squares. So let's look at what that looks like in sum notation. Okay, so looking at this in sum notation, I'm going to give the volume is approximately, now I'm going to need two sums. I'm going to need I to go from 1 to n. So that'll add up all of the, that'll make a column going across. And then j is equal to 1 to m, means that add up the columns. So I'm going to do the height over each square. So that's fxij, yij star, that's the height, times, and then I'm going to use delta A, but we're going to remember that delta A, make that a delta, not AA. Delta A is the same as delta X times delta Y. And we're going to remember that delta X is B minus A over N, and delta Y is D minus C over M. Right, so there we go. Now remember, I can get to the actual volume by taking a limit where both M and N go to infinity of these two sums. So that's basically the same thing with a limit stuck in there. Delta A, right? So we know that by using that, I can change my notation into infinite series. So that's I equals 1 to infinity, j equals 1 to infinity of f of xij star, yij star. Okay, so we work from the inside out. We handle the j's with the y's first, right? So this is going to say that the volume is the sum from I equals 1 to infinity of the integral from c to d of f of xij star, y. And now we're going to make this delta x times dy, right? And then we work our way a little bit further in here. Sorry, that's going to be dy times delta x. And then we work our way a little bit further in, and we get the integral from a to b of c to d of f of xy dy dx. Okay, so this is now a nested kind of double integral here. And it plays exactly as you would expect it to with regard to the fundamental theorem of calculus. So let's kind of give this a little bit of polish with the notation, and then we'll move forward. Okay, so notationally what we can say is we're doing a double integral over our rectangle of f of x, y, d with respect to the area of the rectangle, which is computationally a to b, c to d, f of x, y, dy, dx. Okay, so here's the question. Does the order matter? Okay, do I have to have the CDs and the Y on the inside, the ABs, and the X on the outside? And the answer is no. Okay, so we have a theorem by my favorite mathematician, Fubini. I love that name, Fubini. Okay, so long as if I have R being the rectangle that we've talked about, such that a is less than or equal to x and b, and c is less than or equal to y and d, then if f is continuous on R, which it would be nice if it were, then the volume or the integral over that rectangle of f of x, y, dA is equal to what we said above, a to b, c to d, f of x, y, dy dx. And this is the same as CD of AB, f of x, y, dx, dy. So note, if I switch these, I have to switch the d's at the end as well. And if I do that, I have equivalence, so long as f is continuous over my surface area. Okay, so today we just wanted to get this all, the theory on the table and why it works. In future videos and classes, we're going to go through and look at this in a much more computational way. But that's it for now. All right, so there we go. On to Unit 4.